So lately, I've been working on methods for giving AI assistants better spatial awareness. And it turns out it's actually a really tricky problem. We take it for granted because our brains are really good at creating these 3D representations from 2D input. But with artificial neural nets, it's not an automatic thing, and there's basically two methods for giving the current model spatial awareness. There's the hardcore approach, and there's the naive approach. Now, the hardcore approach is when you actually make the model use 3D data. Now, there's still a lot of ways to do this. For instance, you could actually input 3D data into the model through a 3D scene encoder, and that's what models like Lida and Leo do, but they rely on pre-trained 3D encoders like PointNet. Basically, they encode the 3D point cloud into a sequence of tokens that the autoregressive LLM can actually interpret. Another option is to use 2D images as input to the network, and then have that network generate a 3D representation internally. This is a common approach for self-driving cars and humanoid robots, which represent the space around them as a grid of voxels, kind of like a Rubik's Cube. At any time, each voxel is given a probability of being empty or occupied, as well as semantic classification like tree or car. That sounds simple. I mean, it's just a classification problem. But here's the thing. How do you train that network to predict the voxels? Each element of the data set needs some sort of input image and then also some kind of ground truth for what that voxel grid output is supposed to look like. Generating that ground truth is the part that puts the hard in hardcore. To do it, you actually have to generate NeRFs from the multi-view image set and then use those NeRFs to calculate the loss in the model's output predictions. And doing that at scale takes huge amounts of compute, and it's only feasible for big companies like Tesla. And that's why I'm focusing on the naive approach, which is more of a hack than anything, but it works surprisingly well. Basically, I don't give the model 3D data at all. I just fake it by providing several 2D images of my scene from different viewpoints, and I let the model figure it out. And this only works because the current state-of-the-art models have really, really good image encoders. It's like this wouldn't even have worked just a year ago, and I'll show you why. So take a look at this reference sheet. There's 10 fake people here, and we have an image of one of those people in a totally different setting. Now, for most people, it's trivial to identify which of these people it is, but remember the golden rule. If it's easy for humans, it's hard for AI. At least it used to be until some really big unlocks happened in the computer vision world, and now all the frontier models can do zero-shot classification, and that's honestly kind of a big deal. It's basically the reason that this hack works. Okay, so what am I actually doing? Well, like I said, the goal is to give the assistant better spatial understanding. To do that, I need to give it multiple perspectives of my surroundings, but I don't want to walk around looking like the Dr. Octopus of cinematography. So instead, I just fake it. I make a digital twin of my apartment. Now I can put perspective cameras wherever I want, and I can even let the AI assistant control the camera position. Now, I know what you're thinking. How is the assistant going to know where I am in the digital twin? That's why I'm wearing this. This is a Vision Pro that has a really, really good SLAM system built in, and so all I have to do is put a 3D model of myself in the digital twin. Then when I start the app, I set the position of digital me to the position of real me according to the Vision Pro's estimation in world space. And not only does this work on the position of the device, but I can also track where my hands are. See, here, now I'm not totally rigor mortified. Alright, so now that I have this digital twin working, what can the assistant actually do? Well, the first thing is I can leverage the model's internal visual understanding that's already baked into the parameters. So for example, I can ask questions like, what am I looking at right now?
You're looking at a living room area, a sofa with a blanket, a coffee table with
now
a
that's
book.
cool, but you can also ask questions that require the model to do some spatial reasoning. For example, is there a stove in here somewhere? Where is it?
Yes. The stove is in the kitchen area to your left from where you are now.
Okay, so I'll go left. And we can actually see this working. See, this is my view of the digital twin, and we can see that there's a stove right here. The model was right. So you can see how something like this could actually be really interesting for indoor navigation where GPS doesn't work, like if you're trying to find where the couches are in the IKEA. Now this got me thinking that there are some things that have an important significance or meaning to me, but aren't baked into the model's parameters. So I came up with this idea that I call semantic objects. These are virtual objects that are visually and semantically distinct from one another. Their representations exist in the digital twin, but they're tied to things in the real world. They're basically a dictionary where the key is a 3D object and the value is the meaning that the user defines for it. So, for example, I can ask, what am I holding right now? And the model is going to be able to tell that this is my favorite coffee cup. Now, semantic objects don't just have to represent physical objects. They can actually represent concepts as well. For example, I can ask something like, was there anything I was supposed to do in here?
Yes, you have a chore flagged in the kitchen. Likely the dishes in the sink. You also have a stack of important documents at your desk you may need.
Now, as a person who enjoys the mountains, I'm also interested in how these assistants can help me while I'm rock climbing. Let's pretend that I'm on the last pitch of one of my favorite routes on Mount Yamnuska. It's called Dream Bed. All right, cool. It looks like there's a lot of options here, and I'm not totally sure which way I'm supposed to go, so let's see if the assistant can help me out. Hey, could you describe where I'm supposed to go with this part? I'm a little lost.
With your right hand, reach to the jug just up and right. Bring your right foot high under it, hips right, then match hands on jug to settle. From that stance, follow the diagonal line of small crimps trending up left.
Okay, yeah, that sounds good. I can probably make that work. Now, in the apartment examples, I didn't actually give the model an image of the semantic objects. I just gave it a text description of what to look for. But here, I've actually improved the assistant's performance by giving it a visual reference sheet of the semantic objects that I'm concerned with. These represent different types of climbing holds that are super important to rock climbers, but they aren't baked into the model's parameters yet. This is why I mentioned the zero-shot performance earlier, which is critical for this to work. The model has never seen these objects because I made them, but it's still able to recognize them from a single example. Alright, so far I've just been manually placing these semantic objects in the digital twins to see what's possible with the assistant. But I think the next big unlock is going to be getting the assistant to automatically start placing them and moving them around for you. So for example, you could have a semantic object that represents your car keys, and it could keep track of where you leave them. And since that's an actual object that exists in the digital twin, you don't have to worry about that information leaving the assistant's context window across runs, because it can just query its position even if you're in a completely different place at that time. But anyway, that's it for today. I hope you enjoyed the demo of how I hacked together this spatial AI assistant. Stay tuned for the next one.